Hey, P-Calculus, this is Mr. Szybisty coming to talk to you about Chapter 1.2, Directed Limits and Continuity. In this chapter, we're going to continue to talk about limits, but in this time, in a little bit of a different context. What I've got here is a graph. We're going to give it a name. We're going to call it f of x. And this graph has some interesting characteristics to it. Most notably, it's got a couple different spots where there's holes. You've got this part right here, and then you've got this sort of jump right there. So before I go into too much detail, let's go over a couple of basic things that you've got to know about this graph that you would have learned last year in your pre-calculus class. The first one would be what is f of a. Well, f of a is going to be, you take a look up here, x equals a, and the solid dot is going to give you the function value. That's one. The other one is what is f of b. You take a look up at b, where's the solid dot? It's right here. Again, that is also 1. So this is some stuff we take from pre-calculus. But now we're going to start talking about this in terms of calculus. Namely, we're going to start looking at some limits. So what is the limit as x approaches a of f of x? Well, remember that a limit tells you the behavior of a function. And the behavior of a function really means the height at a particular point. So at x equals a, the area around x equals a talks about that hole right there. And that height corresponds to 2. So this is going to be 2. Remember, the limit has to do with the behavior around that point, not right at it. And that's why we focused on this hole right there and not on this point. So notice here how these two are different. When we have this hole, the function value is different from the actual limit value. Now let me ask you this question. What is the limit as x approaches b? For this one, we would absolutely take a look here at b. But when we look up, the area around b is different. Over here, it's a different height than it is over here. Because this behavior is so radically different, we say that this does not exist. And we write DNE. It means does not exist. And that's because the behavior is different to the left of the point and to the right. That's where our idea of directed limits will come in. It's possible to describe the behavior, but I'm going to have to break it up and talk about the left side and the right side. Let's see the notation for that. To talk about this left side, we would do the limit as x approaches b from the left. From the left, there we are, we're coming from the left to x equals b. What's the height? The height is 3. And then from the right, limit as x approaches b on the right. Here we are, we're coming from the right into the point. What's the height? The height is 1. This is why the limit does not exist. The limit from the left does not equal the limit from the right. When the limit from the left is not the limit from the right, the limit does not exist. This brings us to a point in calculus called continuity. Or you might hear it called a continuous function. Now, what a continuous function means is that there aren't any holes in the graph on a particular interval, and there's no jumps. So, for example, this would be a good example of a continuous graph. This is something that I can draw without picking up my pencil. If you look at our original example up here, there are 2 places where this graph is not continuous. It's not continuous right here because of the hole, and it's not continuous right here because of the jump. But everywhere else, it's continuous. It can be drawn without picking up your pencil. So the question becomes, how can you tell if a particular function is continuous or not? So let me ask this question. Is f of x equal to 3 to the x plus 2 for x is less than or equal to 0, and natural log of x plus 1 plus 3 if x is greater than 0, is that continuous at x equals 1? I'm sorry, at x equals 0. The way that, by the way, we call this a piecewise function because it's got two different parts depending on where you are. For values less than or equal to 0, you use the top branch. If you're talking about something greater than 0, it's this bottom branch. You can tell if something's continuous. There is a 3-condition test. And here are the conditions. 1. The limit has to exist. So the limit as x approaches a has to be equal, a from the right has to be equal to the limit as x approaches a from the left. That's the first condition that has to be true. The second condition that has to be true is that f at that point exists. So f of a has to exist. And finally, the third condition is that the limit as x approaches a has to be equal to f of a. So the limit has to be equal to the function value. If you could show that, then f of x is continuous at x equals a. Let's see that 3-condition test in action here with this example. First, I need to check the limit from the left and the right to see if they are equal to each other. So the limit as x approaches 0 from the left would mean that I'm dealing with the one that's less than, so this. It's a limit, so I just substitute in. 3 to the 0 plus 2, that's 1 plus 2, which is 3. Now I check the one from the right. So the one from the right is going to use the one that's greater than. So I substitute a 0 in, the natural log of 0 plus 1. So this is the natural log of 1. The natural log of 1 is 0. 0 plus 3 is 3. These are both the same, so I know that the limit exists. That the limit as x approaches 0 is 3. I know that it exists, and it's 3. So that is a check for condition 1. Now I need to check condition 2. F of 0, well, I come back up to the original function. I would put the 0 into the top branch because that's where x is equal to 0. This would be 3 to the 0 plus 2, which is 3. So it does exist. It's 3. I've proven condition 2. Now I need to check the last condition. The limit as x approaches 0 of f of x I knew was 3, and that is equal to f of 0. Take a look right here. We know that it's equal to f of 0. Since I know that these two are equal, this is a check. This means that there's no hole or jump at x equals 0, and I can say that f of x is continuous at x equals 0. And that's how I show it with that 3-condition test. There is no jump. There are no holes. Also, the third thing that we know, there are no asymptotes either. It's a nice smooth curve, or a nice curve at that point. How about another example? Does f of x equals x squared plus 2x plus 1 have any discontinuities? So that's our next question. Does this function have any discontinuities? And it requires us to know a fact. Fact. Functions are continuous on their domain. The domain for this function is from negative infinity to infinity, which means that f of x is continuous from negative infinity to infinity. There are no discontinuities. So the answer would be no. F of x is continuous everywhere. This leads us to another question. Where are these functions continuous? And the functions that we are going to have are g of x equals x e to the x plus 3, h of x equals the square root of x minus 3 plus 1, j of x equals the natural log of x minus 4 plus 2, and k of x is x plus 3 over x minus 2. The domain of my first one is all real numbers from negative infinity to infinity, so this function will be continuous from negative infinity to infinity. With h, you have a square root. And with a square root, you can never take a square root of a negative number, which means whatever is on the inside must be positive or 0. So that means that x minus 3 has to be greater than or equal to 0. So x has to be greater than or equal to 3. So if I were to write that using interval notation, this function is continuous on its domain. It has a domain of 3 to infinity. With a natural log, what's inside the natural log has to be positive. It can't be 0 and it can't be negative. So x minus 4 has to be greater than 0, which means x is greater than 4. If I were to write that using interval notation, I would say 4 to infinity. Last but not least, with k, we have a denominator. In a denominator, it can't be 0. So I would say that x minus 2 cannot equal 0. X can't equal 2. If I were to write that using interval notation, I would say negative infinity to 2, union 2 to infinity. And so I know that this g of x is continuous on that, h there, j, and k. A function is continuous on its domain. The last type of problem that I want to show you is one that you might see on the AP exam, and it questions what particular value or values would make a function continuous. So we're given this piecewise function. F of x equals, and then the top is x squared plus kx plus 3, for x is greater than or equal to 3. The bottom one, 2x squared plus 4x plus k, if x is less than 3. The question is, what value of k makes f of x continuous? Well, I know I've got my three conditions that I would have to satisfy. So I'm going to start with the first one. I have to show that the limit from the left and the right would be the same. So the limit as x approaches 3 from the left would be, okay, so the one from the left would be the less than. So I'm going to put a 3 in for x. So this is 2 times 3 squared plus 4 times 3 plus k. So 18 plus 12 plus k, 30 plus k. Now for the right. Limit as x approaches 3 from the right. Now I'm going to put it into the top one. So this would be 3 squared plus k times 3 plus 3. So that's 9 plus 3k plus 3, 12 plus 3k. Remember, condition 1 said that from the left and the right they had to be equal. So that the limit as x approaches 3 from the left equals the limit as x approaches 3 from the right. That's the way to show that the limit exists. So, from the left has to be equal to from the right. What value of k would make that possible? So set them equal to each other. 30 plus k equals 12 plus 3k. Well, this would end up being 2k is equal to 30 minus 12, which would be 18, so k equals 9. As long as k is equal to 9, the limit would exist. And you could double check condition 2 and 3 to show that the other two conditions would be met. But this type of problem would more than likely be a multiple choice problem, and once you found the k, you'd be all set. You can double check the other options if there are any on the problem. So that's chapter 1.2. Make sure that you write your summary and you formulate your questions, and I will see you in class the next day.